if Chapter 3 kinematics was talking about motion without talking about the forces that cause the motion, dynamics was study of motion, but specifically we focus on the forces that cause the motion. This new chapter, forces, density, and pressure, is more on the other effects of force, okay, not just on motion. All right. So this one is more focused on other types of forces. Okay. So when you're talking about forces, you know that there are always forces that oppose the motion of an object. In your syllabus, there are actually two kinds of forces that will oppose the motion of an object. The first one is called friction. The second one is called drag force. Okay. Both will oppose motion, but the manner in which they act is a bit different. Okay. For example, if you have an object that is pushed along a surface, eventually it will come to rest because of friction. Okay. Now, friction will always resist the motion of an object whenever there's relative motion between two contacting surfaces. When we talk about friction here, it's mainly the opposing force that arises when you have two surfaces rubbing against each other. Okay, when you have two surfaces rubbing against each other, there is relative motion between them. Okay, so when you have relative motion between two contacting surfaces, that's where you start to have friction. Okay, is what opposes the motion of an object, is what causes an object to eventually come to rest. Okay, now friction depends on the nature of the contacting surface, whether it is smooth or rough. You know that if the object is smooth, there's no friction, but if the object is rough, there is friction. Okay, and it also depends on the degree to which they are pressed together. Okay, so basically it depends on the normal reaction force. Now, this one won't really be covered in physics, but it will be covered in maths under the mechanics paper. Generally, what we'll tell you is that if you have an object that is resting on a flat surface, you know that there is weight. You also know that you have a normal reaction force, okay? So the thing here is that what you will eventually learn in your maths mechanics paper is that friction can actually be calculated by using this equation, mu n. Mu is actually some sort of constant called the coefficient of friction. Then this one is your normal reaction force. Okay, so friction actually depends on your normal reaction force as well as the constant that you have here. So the harder you push them together, the more you press them together, the bigger your N, the bigger your N, the bigger your friction. Okay, so friction here, you can just roughly think of it as this. If you want to have more friction, just make sure that the surface is rough and also you press them together even more tightly. Okay, but the one that we will normally test you on for physics is this one. If the surface is smooth, no friction. If the surface is rough, there's friction. The part where we talk about the normal reaction force, the effect of normal reaction force on friction, this one we won't test you. This one is something that you will learn eventually later in the maths mechanics paper. Okay, so friction depends on nature of contacting surface and degree to which they are pressed together. It is independent of your contact area and is always proportional to the normal reaction force, like what I just mentioned to you just now. Okay, because F friction is equals to mu n. So F friction is proportional to n. Okay. Now, frictional force is always assumed constant regardless of speed. Okay. When you do your questions and then they tell you that the moving object encounters friction, always assume that that frictional force is the same, regardless of whatever speed of the object is. Because sometimes you may come across a case where your object was moving at 5 meters per second, and then after that, it moved up to 20 meters per second. All this while it encounters a frictional force of, say, 1 Newton. You always assume that the frictional force is always the same. Okay? So that is what frictional force is. Now we move on to drag force. Drag force also opposes motion, similar to friction. But how they come about is not because of having two surfaces rubbing against each other. It comes about mainly because you have an object that moves through a fluid, such as air, water, or oil. Any fluid. Fluid is just simply gas or liquid. As long as you have an object that moves through fluid, moving through gas, moving through liquid, it will always encounter resistance to its motion. That one isn't called friction. That one is called drag force. Okay? So here, what we will tell you is that drag force is directly proportional to speed. It is not constant. It will change with speed. Okay? Drag force is actually also, air resistance is actually a form of drag force. Remember before this in the chapters, before this, when you were doing kinematics, I told you that air resistance is directly proportional to speed. The faster you go, the more your air resistance. That's because air resistance is a form of drag force. Okay, it will change with speed. So if I refer back to the object that I have here just now, if I tell you that as the object moves, it has an air resistance of, say, 3 Newton. Once your speed becomes larger to 20 meters per second, your air resistance is not going to be constant. It will be larger. It will increase. Maybe now it's 8 Newton. Okay, so this is the difference between drag force and friction. Both will oppose motion, but the way they come out is different. One is through rubbing of two surfaces, another is through moving a fluid. And then frictional force is constant, drag force increases with speed. Okay, so that is what drag force actually is, and that's what friction and drag force actually is. So this one, I'll just write it here. This is motion. Okay, so use a different color. Okay, so this is one thing. Okay, now drag force increasing with speed is what actually causes a falling object to eventually achieve terminal velocity. This one is what we went through in kinematics, how an object actually achieves terminal velocity. So that one I don't really need to explain so much anymore. Okay, now what affects drag force? A drag force is affected by the surface area as well as the fluid viscosity. Okay, now fluid viscosity, let me just write out certain things.
Sorry, sir.
Yeah.
I just want to ask, is today's class 1.5 hours or 2 hours?
I'm not too sure. It can be 1.5 hours, it can be 2 hours. So are you planning to have it at 1.5 hours or 2 hours?
I'm okay with anything. I was just asking.
Yeah. I think we just make it 2 hours now, all right? Okay. Unless maybe by 4 o'clock you feel that you feel very tired already and you want to call it a day, just let me know. It can be 1.5 or 2 hours. Okay.
It's okay. It's okay. We can. I try to do too.
Okay. Right. So no worries. Okay. Now let's go back to this one. Drag force is affected by fluid viscosity. Now, fluid viscosity is referring to how thick the liquid is. Okay, now if I ask you to compare between water versus maybe syrup, okay, if I ask you to compare between water and syrup, and then I ask you to pour them, maybe let's just say that this is a beaker, and then you have something here. I ask you to pour the liquids out into this little container here. Now, which one do you think will actually flow smoother, water or syrup?
Syrup.
The syrup will flow slower, right? It feels more
Yeah.
difficult to pour it out, right? But if you talk
Yeah.
about water, water is very easy to pour out, right? So that is what we mean by how thick the liquid is. The higher the fluid viscosity, the thicker it is. So it's harder for it to flow. Maybe let me just write this is harder for it to flow. Okay, it's harder for the liquid to flow. Okay, another way to think about how thick of a liquid is that if you have a spoon, if you have a spoon and then you dip it inside the beaker containing water or syrup, the water is easier to stir with the spoon, but the syrup is harder to stir with the spoon because the syrup seems to be opposing your motion, isn't it? It's thicker, it's harder to flow, so you seem to need to exert more effort to stir it. It's like it's as if you're encountering some sort of resistance to move your spoon through your syrup. Okay, so drag force is related to how thick the liquid is or the fluid viscosity. The thicker it is, the harder it is for you to move. The harder it is for the liquid to flow, you will need to exert more force to move through it. Okay, that's why here we'll say your drag force is actually higher because you need to exert more force to move through it. It is opposing your motion through the fluid. Okay, and then another thing will be surface area of object will actually cause a higher drag force. This one, I think this one should be easier to see. It's more like this one. If let's just say I talk to you about dropping something in the air, if you have a ball that is maybe 100 grams, and then you have a flat piece of plank, maybe this is ball, and then this one, maybe I say is styrofoam, also 100 grams. You drop it, you drop both of these objects from the same height, they will encounter air resistance, but this one will say to you that the air resistance for the styrofoam is actually larger. If I tell you that this is RA, and I tell you that this is RB, maybe this is object A. Sorry. Maybe I tell you that this is object A, and this is object P. Okay. We will tell you that RB is actually more than RA. Even though you have an object with the same mass, released from the same height, released through the same fluid, when these two objects drops, the object with the higher surface area will actually experience a higher drag force. Okay, so surface area will actually affect the amount of drag force that you encounter. If you're talking about the ball, the cross-sectional area is just this. But you're talking about the styrofoam, the cross-sectional area could be something like this. So this one, larger area, larger drag force. Okay. So these are the two things that could affect drag force: viscosity of the fluid and surface area of the object. Okay. So another thing I probably should mention is this. Yeah, the RB is more than RA because B has larger surface area perpendicular to perpendicular to airflow. Perpendicular to the motion. Okay. So surface area of the object, when we talk about the surface area is normally the surface area perpendicular to the motion. Okay. So this one is my motion. This one is also my motion. When we talk about the area, we talk about the area that is perpendicular to your motion, which is this one here. Okay. So there is drag force. Okay, so these are just two introduction to forces that oppose motion, drag force and friction. This one don't worry so much about it. We don't really test you that much on it. Now the one that we will really test you is the third force called upthrust. Okay, so upthrust is actually the vertically outwards force acting on an object that is immersed in a fluid. It arises due to difference in pressure of the fluid at the top and bottom of the object. Okay, so let me just clear off everything here and explain to you what is upthrust. Now, upthrust is what allows an object to float, okay, in water. So if you have experience going into a swimming pool before, you will notice that once you wade inside the swimming pool, you somehow feel lighter. It's as if something is helping to push you up. That is what upthrust is, okay? Any object that is immersed inside a fluid, like liquid, such as water, will experience upthrust, okay? It is a force that allows an object to float in water in the first place, okay? So it is also the force that you experience when you try to go inside a pool or river, you suddenly feel lighter. That is upthrust acting on you, okay? Now, upthrust arises because of the difference in pressure at the top and bottom of the object that was immersed inside the fluid. What do we mean by that? Is something like this. You will need to know how to derive upthrust, the equation for upthrust. Okay, it is normally based on a diagram that looks like this. So now let's just first consider that you have an object that is immersed inside the fluid, a liquid. Okay, the object has a volume of V. Okay, and then after that, the height of the top and bottom surface is at H1 and H2 respectively. Okay, so you have an object, you immerse it inside a fluid with density rho. The top surface is at the height of H1, the bottom surface is at a height of H2. Okay, so right now, if we ask you what is the pressure at the top surface, you know that pressure is equals to H rho G. So if you apply it to this top surface here, it will be P1 equals to H1 rho G. If you apply that same equation to the bottom surface, you also find out what's the pressure at the bottom surface. The pressure at the bottom surface will be P2 equals to H2 rho G. Okay. Now, the pressure acting over an area of the object will cause a force. If I try to draw it in 3D for you, this object here, you can maybe think of it as being similar to a cube, maybe. Okay, you have an area here. Okay, so the pressure acting over an area gives you force. So you know that pressure is force over area. So force is pressure times area. So what's the force acting at the top and bottom surface? You will say that at the top surface, F1 is P1 times A. At the bottom surface, F2 is P2 times A. But here, you already know what is the expression for the pressure, so you sub it back in, you get this expression instead. Okay, so this is an expression for the forces at the top and bottom surface of an object that is immersed inside a liquid. Now, another thing here would be, if we ask you between force F1 and F2, which one is actually the larger one, we will tell you that F2 is larger than F1. Simply because H2 is more than H1. Okay, because we want to make a comparison between the two forces, rho G and A are actually the same. So F is actually directly proportional to H. The larger the H, the larger the force. So since H2 is larger, F2 is larger. Okay. Now, from there, there's another thing. You know that there's force F1 acting at the top surface and force F2 acting at the bottom surface. The direction of the forces are also different. F1 will act down on the top surface. F2 will act up on the bottom surface. Okay, because pressure, you know, acts in all directions. So if it acts in all directions, the top surface will have the force acting downwards. The bottom surface will have the force acting upwards. Okay, pressure acts in all directions. Top surface, pressure acts downward, force also acts downward. Bottom surface, pressure acts upwards, force also acts outwards. So since you already established that F2 is more than F1, this follows that you have a resultant force upwards. Therefore, there is a resultant force upwards. Okay, that is what you can see here. This is upthrust. Okay, that's why here we say that upthrust is the vertically upwards force acting on an object that is immersed in the fluid, which arises due to the difference in pressure of the fluid at the top and bottom of the object. The difference in pressure causes a difference in force, and the force is larger at the bottom and is acting upwards. This causes a resultant force upwards, which you know as upthrust. This is what allows an object to float. This is what makes people feel like they're lighter inside a pool. Okay, so the upthrust is actually that resultant upward force. You want to find that resultant upward force, you will just take F2 minus F1. And since you already know what's the expression for F2 and F1, you get this H1, H2 rho GA minus H1 rho GA. Factorize rho GA, you get H2 minus H1. Now H2 minus H1, you notice is going to be this. If this is H1 and this is H2, H will just be this. So it becomes H rho GA. And then if you try to play around again with the expressions there, remember just now I tried to draw something here where I told you that this one is A. If you have H and then you multiply with A, this will give you volume. Okay. So your resulting expression will become V rho G. Okay. Now,
Yes.
V rho G will become mg because it comes from this. Rho is m over v, m is rho v. So it becomes mg. Now the thing here is that you can recognize that this mg is an expression for weight. But my question to you here is that, is this the weight of the object or weight of, maybe I just write liquid displace now, of liquid displace. The expression rho v here is mass. Multiply with g, it is equals to weight. Yes, that one we know. But what weight is it? Is it the weight of the object or is it the weight of the liquid displaced?
Weight of the liquid displaced.
Yes. How do I know it's the weight of the liquid displaced? Is because of this. This one is the density of the liquid. Density of liquid multiplied with volume of liquid displaced gives you the weight of liquid displaced. The volume that you have here is correct to say is the volume of object, but it's also correct to say is the volume of liquid displaced. If say your object had a volume of 100 centimeter cube, you will also be displacing the same volume in the liquid. Okay, so the V here, although you see is H multiplied with A of the object, it can actually represent two kinds of volume. Is firstly the volume of the object, is also the volume of the liquid displaced. But once you multiply with the density, where the density here is clearly density of liquid, it is telling you that it is mass of the liquid displaced. Multiply with G, you get weight of the liquid displaced. Okay, so this mg here is not the weight of the object. It is the weight of the liquid displaced. Okay, so upthrust in general is the weight of the displaced fluid, which is rho Vg, which is also sometimes known as Archimedes principle. Okay, but in your syllabus, we won't ask you what is Archimedes principle. It's something that you learn in IGCSE. We just need you to know that upthrust is actually the weight of liquid displaced. That's all. Okay, have a look at page 2, question 14. Okay, now you have 4 cuboids with identical lengths, breadth, height that is immersed in water. The cuboids are held at the same depth and are in identical orientations by vertical rods as shown. Water has a density of rho. Cuboid W, X, Y, Z have densities of 4 rho, 2 rho, and 0.5 rho respectively. What statement is correct? Which of this statement is actually correct? A cuboid is just something that looks like this. Okay. So what do you think is the correct statement here?
I think it's either B or D.
Okay, it's either B or D. Okay, so the one the correct statement, yeah. Okay, the either B or D, this one is wrong. The correct answer is A.
Huh?
Right. That's why I told you. Remember what I mentioned to you about upthrust? Upthrust is the weight of liquid displaced. Liquid displaced. Okay. Weight of liquid displaced. Now, they told you here you have 4 cuboids with identical length, breadth, and height. And basically, this statement already tells you that the 4 cuboids have same volume, isn't it? If I can tell you that this one is the length, wait, maybe I'll tell you that this one is the length, this one is the breadth, and then this one is the height. If the cuboids have the identical length, breadth, and height, that means they have the same volume. Okay, so when they have the same volume, that means you have the same volume of water displaced. So when you have same volume of water displaced, therefore, same weight of water displaced, therefore, thus, I'm just right, thus, same upthrust. If this one is 10 centimeter cube, this one will be 10 centimeter cube, this one will be 10 centimeter cube. This one will also be 10 centimeter cube. They will all be displacing the same volume of water. So if they're displacing the same volume of water, that means you are displacing the same weight of water, which means you are displacing, which means that you have the same upthrust. Okay, now you look at the cuboids W, X, Y, and Z. You see that they have different densities, right? Now, what does the different density affect? This one here, the different densities affect the weight of the cuboids themselves. Maybe I don't like themselves. The different densities here affect the weight of the cuboids only, not the water displaced. Okay, so when you're talking about the upthrust of water on W is twice the upthrust of water on X, is mainly because I think you see that this is double this one, right? That one, because the density is more than this one, it's not to say that your upthrust will be double. This one is not correct. It will be more correct to say that the weight, oh yeah, this entire term is wrong. This statement B is wrong because of this, because it's saying the upthrust of water on W is twice the upthrust of water on X. It's not supposed to be upthrust. You would have to say that the weight on W is twice. This entire statement, let me just write the proper statement for you. It's hard to modify this. The correct one is weight of W is twice of X. Then this one will be correct. Then the upthrust on, if you look at D, the upthrust on water Y, the upthrust of the water on Y is 0. This one is nonsensical. This one, the upthrust on water on Y is 0. And this one cannot be true. This one, as long as there is volume displaced, there is upthrust. Okay, so B and D is definitely out. B, you see that W has double the density of X. It merely means that the weight is twice. That's all. It doesn't affect anything on the upthrust. And in D, they tell you say that the upthrust of the water on Y is 0. That is not true, because you can clearly see here Y is immersed inside the water. There is volume of liquid displaced, and that volume of liquid has weight. So it will have upthrust. It cannot be 0. Okay, so answer C therefore must also be wrong. So let's just see why. Upthrust on water X or water on X is twice the upthrust on water on Y on W. It's the same thing again, because you see this one is double the density of this one, right? It's not correct to say it's the upthrust that is double. It's more accurate to say that weight of X is twice of Y. Then these are the correct statements. Okay, so answer is A itself. It may look different, everything, but they're actually the same in terms of the upthrust. The upthrust of water on each of the cuboids is the same. Okay, so this one.
Okay.
So this is for upthrust. Okay, so this is the main thing. As you always need to look at
Okay,
the
sir.
weight of
Yeah.
volume displaced for upthrust. Okay, so that one is okay. That is page 2, question 14. We move on to page 1, question 14 again. All right. You have a ladder that is positioned on an icy frictionless ground and is leaned against a rough wall. At the instant of release, it begins to slide. Which diagram correctly shows the directions of the forces P, W, and R acting on the ladder as it slides? Okay, so this one, they want you to identify correctly all the forces that act on the ladder right now. So there are a few key things here that you can try to see. They tell you that this is positioned on a frictionless ground and placed on a rough wall and leaned against a rough wall. Okay, so they release it and then it now begins to slide. So what are the correct forces that show the situation right now? So if you see that it's frictionless ground, that means this one, no friction. Rough wall, this one has friction. Okay, we talk about friction now because it is because there's motion between two contacting surfaces. We won't say it's drag force because you have nothing that's moving through the fluid right now. You have contacting surfaces that are rubbing against each other. So if you look at the diagram right now, if I were to draw it as a separate diagram for you right now, this is your wall and your ground, and then this is your ladder. Okay, this is, sorry. This is your ladder. Okay, there are a few forces here. You know that weight always acts down. So I know W will be this one. Okay. Then after that, another thing that you should know is that normal reaction force arises when an object pushes onto a surface. Okay. Normal reaction force arises when an object pushes onto a surface. It is always perpendicular to the surface. Okay, this is normal reaction force. In case you're wondering what normal reaction force is, I didn't write this in the notes, but I think this is something that you all must have learned before. Okay, so a normal reaction force will arise when an object pushes onto a surface. It will always be perpendicular to the surface. So now let's just say right now, if I just want to single out normal reaction force, the ladder, if I talk to you about the ladder right now, this part here, now when the ladder wants to slide, it will move like this, right? From this position, it will suddenly move to this position, right? Correct? From the first position here, it will go to the second position, it will go to the third position, right? That's how a ladder will slide, right? It's not going to slide down, it's going to slide down. All right. So right now, if I just look at the first position here, is the ladder pushing against the wall? The red circled portion here. Is it correct to say that the ladder is pushing against the wall?
No. It's like slanted.
Yeah, it's slanted, it's leaning against the wall. You could say that it's pressing against the wall, right?
Yeah.
Right? So because this portion here that I circle is pressing against the wall, you would have a normal reaction force N, perpendicular to the wall surface. That one is okay. Now, if I move on to the next N, which is this one, You could also say that this end of the ladder is pressing down on the ground. Okay, so because it's pressing down on the ground, you also have a normal reaction force perpendicular to the ground. Okay, so this is what's happening here. You identify the normal reaction force. And then the last thing I want to talk about is friction. Okay, so we learned already that friction always opposes motion. Okay, that is the main thing about friction. Okay, it always opposes motion when there are surfaces rubbing against each other. Okay, so we know that at these 2 points that I circle here in red, the ladder is rubbing against the wall, is rubbing against the ground. So they, by right, should be friction. Okay, but if you look at the question carefully, they really told you that the ground itself is icy, is frictionless. So this one I know that there is no friction. Okay, yeah, before I go any further, let me just identify for you the motion at both ends of the ladder. Okay, now if you look at the left hand part, this one, the ladder is actually trying to move down, right? This is the motion for the ladder. When the ladder tries to slide like this onto the ground, you can try to predict what is the direction of the ladder at both ends. For this side here, the ladder is trying to move down. For this side here, on the other end, the ladder is trying to move here. Okay, so now I want to identify whether there's any friction. I already told you that the bottom end here at the ground has no friction because it's a frictionless ground. Okay, so I know that there is no friction here. But what about the case at the wall? The wall is rough. It therefore must have friction. If my motion is downwards for the ladder, friction must oppose my motion. So my friction should actually be acting upwards. This is my force of friction. Okay, so far can follow what I'm talking about?
Yes, sir.
Yeah, okay. So when you want to identify whether there's friction, you just look at the motion of the object. Where is it going? And then once you identify where is it going, you know that friction must always oppose the motion. It will be acting in the opposite direction. So that's why here I can come to this conclusion that friction is acting upwards, and then this one has no friction in the first place because it's a frictionless ground. Okay. Okay, now, so from here, if I look at the top part of the ladder, I have 2 forces. Is it correct to say that these 2 forces will give me another resultant force? Can I combine these 2 forces to give me a resultant force? Yes, no? This
Sorry,
one,
sir, I couldn't really hear you. It was like a bit laggy. I think it's my Wi-Fi is not that good because it's raining really heavily.
oh, okay, right, no worries. I'm just asking you whether at the top part, at the wall, the frictional force and normal reaction force can give you a resultant force. Is it correct to say that I can combine those 2 forces into a resultant force? Yep. Hello? Oh, okay. So you still can't hear me. Okay, is this better now?
Yeah, yes. Can you hear me, sir?
Yeah, I can hear you. All right, I can
Okay.
hear you loud and clear. Okay, so you can hear me now. All right, so back to what I was just asking you. If you look at the top right hand, the top left hand corner, the one near the wall here, I have a force of friction and I have a normal reaction force.
Yeah.
You can actually combine those two forces into a single resultant force, right? That's what you learn in chapter 1. Whenever you have any forces acting, any vectors acting, you can often combine them into a single resultant vector. So right now, my question is that if you combine the frictional force and the normal reaction force, what do you suppose is the direction of the resultant? Is it this one? Is it this one? This one or this one? Let me just label it for you. A, B, C, and D. Where do you suppose is the direction of the resultant? A, B, C, or D?
I think it's B.
Yes, correct. Because remember, if you try to draw the vectors from head to tail, this one is N, this one is force of friction. The resultant will be from the first point to the last point. So the correct direction should be B. All the others are actually not correct. So right now, what you will have is a force here, P. Okay. The reason why I put this P is because they label the forces here P and R. Okay. Right. So this one is your force P. Now, if I then single out the bottom portion right now, my resultant force, is it correct to say that my resultant force is actually just N itself? There's no other forces, right?
Yeah.
Right? So this one would actually be my R. Okay, I'm just using back all the symbols that the question has given you. They say force at P, force on the wall is P, force on the ground is R. Okay, so this is the actual situation right now. This is the actual forces on the ladder right now. So when you look at answer choice A, B, and A, B, C, D, which one do you think is the answer?
I think it's B.
Right, so the answer for this one is B. Okay, so that's how you would do this question. You have to identify the forces one by one and then see how they are. Okay, so for this one, what about the answer choices A, C, and D? I can actually just elaborate a little to you. Okay, now for A, R is like this. I know that this one has no friction. Now for P here, the reason why P is like this is also again because there's no friction. Because you see here from the diagram that I already drew for you here, how do you see the directions is that you identify first all the forces at the ground as well as the wall. So if here you see for answer choice A, P is just horizontal only, that means there's no friction. It's only when you have friction that you have a resultant force like this. Okay, so A is telling you that both ends have no friction. This is not what the question is describing. Only one side has no friction. One side has friction. So this one is saying that both sides have no friction. This is wrong. Now, if I look at C, P is horizontal. This one means that there's no friction. The P itself is just the normal reaction force. But for R, when you see like this, notice that it's diagonal already. It can only be diagonal if in the first place you have a normal reaction force and you have a force of friction here. This one here is saying that you have friction. Okay. Again, this is not the case that the question has described to you. So A and B is out. A and C is out. Now you look at D. D is a bit nonsensical. So if you look at the wall, the only time you can get a force that's in this direction is if your N is here, and then your force of friction is here. And then the only time you can get an R in this direction is again when you have a normal reaction force like this, but this time your force of friction is like this. Okay. Now there's something wrong with this part particularly, because this one is telling you if I try to identify the motion of both ends of the ladder, let me just use green color. To get a force of friction in this direction, that means the motion must be downwards. Whereas this one, on the other end, to get a force of friction towards the right, my motion must be opposite. It must be this one. Now tell me, does this motion make sense? The ladder now, basically what this diagram is telling you is that the one end of the ladder is moving, is trying to go down, another end of the ladder is trying to go in. It doesn't make sense in real life, right?
Cannot move that way.
Yeah, I can't move that way. So this one here is just simply not sensible. Okay. So the answer is just B. Okay, so that is for this one, right? This is just looking at the forces. Okay, then there's some other stuff here that we can do. All right, I'll just go a little bit more from the notes. This one talks about center of gravity. This one talks about terminal velocity again. All right, so if you look back at the notes under page 2, now under the chapter of kinematics, I really kind of explained to you how terminal velocity is achieved. So remember that time I mentioned to you under the chapter of kinematics, under the chapter of kinematics, when we are talking about terminal velocity, I told you that you have an object that falls, and then when you have air resistance taken into account, as the object falls, let's just say that this is the motion. As the object falls, it encounters air resistance. So the key take-off point was that R increases with speed until it is equal to W. So at that time, your F net will be equals to 0. Velocity acceleration is 0. A is 0. And V is constant. So that time I mentioned to you that your graph for velocity time and acceleration time for something that achieves terminal velocity is something that looks like this. Okay, where this one itself is actually your terminal velocity. This part here, you have actually reached terminal velocity. Okay, so you should roughly remember bits and pieces of what I mentioned. Basically, terminal velocity was achieved because you have air resistance opposing your motion, and then the air resistance will increase with speed until it's equal to your weight. So when it's equals to your weight, your net force will become 0, your acceleration will become 0, you start to move with constant velocity, which is this one here. Okay, so here we also have something on terminal velocity again on this chapter. But the thing here is that we will tell you is that now is that you have another force to consider. Okay, so if you have an object that moves through a fluid, let me use a different color. If you have an object that moves through a fluid, it will also achieve terminal velocity when drag force and upthrust is equal to the weight of the object. In kinematics, that time when we were talking about terminal velocity, this one was the case where it was falling in air. Now in this chapter, we also talk about terminal velocity, but this time you have an object that is falling in liquid, okay, or fluid lah. Okay lah, I just say falling in liquid lah, right? Falling in liquid, all right? This one maybe, yeah, this one maybe rather than you saying fluid, you can just change it as liquid lah. All right, an object moving through a liquid achieves terminal velocity when the drag force and upthrust is equal to the weight of the liquid. All right, so we also have a case where an object can achieve terminal velocity if it's falling in the liquid, but the forces you consider is slightly different than when it's falling in the air. You have to consider the presence of upthrust. Okay, now just now I mentioned that upthrust is the weight of fluid displaced, right? Okay, why is it now that in the case in kinematics, when the object was falling in air, we did not consider upthrust, but over here, when we say that it's falling in a liquid, we need to consider upthrust. It's because of how your upthrust is defined. Now, you see, upthrust is actually weight of liquid, sorry. The correct term is actually weight of fluid displaced, which is actually rho Vg. Okay. This one is the density of the fluid. Now, you can see from here that upthrust is actually proportional to density. The higher your density, the higher your upthrust. Okay, so what we'll tell you here is that upthrust in gas such as air is negligible. But then upthrust, sorry, this one upthrust in gas, okay. But upthrust in liquid is significant. Now, why do we say this? If I ask you what's the density of air, density of air is just 0.5 kg per meter cube. Okay, 0.5 kg per meter cube. But if I ask you about density of water, it's about 1000 kg per meter cube. So you see, when you compare between those two, air and water, because air is having a very little density, the U is very, very small. That's why we say that we can ignore it. It's negligible. That's why here, when you're talking about terminal velocity for an object that's falling through the air, upthrust is negligible. We don't consider it under the analysis. But you're talking about something that falls inside liquid like water. You see, this one is 1000 kg per meter cube. So U is very large. Cannot be ignored. Okay, so that's one thing that I would just like to mention to you. Why is it that now suddenly we need to consider upthrust? It's because when you're falling in liquid, upthrust is significant. You have to consider it too. All right, so that was one part here. So here, for an object that's falling through a liquid, an object will still achieve terminal velocity. It will eventually reach a constant maximum speed. Again, because you have something that again, because you have something, the opposing force increases such that it's equal to weight. Yeah, another thing here that I should also mention is that when your object is falling through a liquid, rather than saying that you have air resistance opposing you, you have drag force. Okay, so the diagram is something like this here, that's written here. So what would happen is that if you have an object that you release inside water, initially, let me just clear also. I just read from the diagram that I have here. Initially, if you have an object, you release it from rest, it has weight 200 Newton, and then you have an upthrust of 50 Newton. As I mentioned, upthrust is significant. When you release it from rest, there's no drag force yet, okay? You haven't started to move, you have no drag force opposing your motion, okay? Weight is larger than your drag force, so your object will accelerate, okay? So right now, your F net is actually 200 minus 50 is 150 Newton, okay? But then once you start to move, you have drag force that starts to arise. In addition to your weight and upthrust, you now have drag force opposing your motion. So right now you have a drag force of 50 Newton. Your net force is now going to be 200 minus 50 minus 50, you're going to get 100 Newton. Okay. So from here, to here, from here to here, your F net decrease, your acceleration decrease, the object speeds up, but at lesser rate. Okay. From 150 Newton to 100 Newton, your net force has decreased, your acceleration has dropped. You're still speeding up, but at a lesser rate. Okay. So because you're still speeding up, but at a lesser rate, the main thing is that you're still speeding up, your drag force will continue to increase as the object speeds up. So rather than it being 50 Newton here, it suddenly increased to say maybe 120 Newton. Okay, so as a result of that, your resultant force decreased even more, your acceleration decreased even more, but you're still speeding up, but at a lesser rate. Okay, so what will then happen is that your drag force will keep increasing until such a point that your drag force and upthrust are equal to the weight. There will be no resultant force here, your acceleration is 0, your object will now fall at constant terminal velocity. So here, let me just try to draw something else again. Here, your F net is 50 plus 120, so it's 170. 200 minus 170, you have 30 Newton. So you can also say the same thing here. This one here, your F net decrease, your A decrease. So object still speeds up, but at lesser rate. Okay, so your drag force will keep increasing until drag force and upthrust are equal to weight. So here, when you see that the sum of upthrust and drag force is 200 and your weight is really 200, your net force here is 0. So your A is 0, your V will be constant. Okay, this is where you reach terminal velocity. Okay, so this is also talking about terminal velocity again. But for the case of an object that is falling through liquid, the only thing different now is that you have upthrust to consider, and the force that opposes your motion is not air resistance, but rather drag force. Okay? It's only when you're talking about moving in air that you have air resistance. But if you're moving in something else like a liquid, it's called drag force. Okay, so this is terminal velocity again. Okay, now there's one question here that we can somehow look at. If you look back at your worksheet, question 3, sorry, page 3, look back at your worksheet, page 3. Okay, this one talks about something that is moving with constant velocity, something like terminal velocity again. Look at page 3, question 15. You have an air bubble in a tank of water that is rising with constant velocity. The forces acting on the bubble are X, Y, and Z as shown. What describes the three forces? Now, there are a few key things here that you can see. If you are rising up, there are actually three forces here. Your viscous drag, your weight, and your upthrust. Okay. So your viscous drag is actually your drag force. Okay, sometimes they may not call your drag force as that term, they call it as viscous drag. It's the same thing. So now if you see that you have an air bubble in the tank of water that's rising with constant velocity, the fact that it is rising and the fact that you have a drag force acting on it, the direction of your drag force must be acting downwards. Okay, so this one here is the first thing you can see. Drag force must be downwards to oppose motion. Okay, I know the drag force must be downwards. Okay, so another thing you know is that weight is always downwards. Weight is always downwards. Upthrust is always upwards. Okay, so you establish now that there are a few things. You have something like this. Weight is downwards. Your viscous drag must be downwards. And then you have upthrust upwards. This is the direction of the forces right now. Now, there's another thing here that will tell you something else. If your object is at constant velocity, this tells you that no resultant force. Okay, F net is equals to 0. So from this diagram that you have here, you can say that W plus R must be equals to U. Okay, so this is what you have. Now, if you look at the answer choices A, B, C, and D, oh yeah, this one here, the question did it a bit different for you. They tell you that weight is Y, Z is the viscous drag, and then X is the upthrust. So if I rearrange this one for you, this one will actually be Y plus Z equals to X. Okay. Now, if you look at these answer choices, which one should be correct? A, B, C, D?
A.
A. Okay, so you say it's A. Okay, let's try and see. Okay, Z is the viscous drag of the bubble. Y is the weight of the bubble, and X is the upthrust of the bubble. And X is equals to Y plus Z. Okay, that is okay. Why can't it be D?
Because there's no resultant force, so it cannot be like X is more than Y plus D.
Oh, yeah. Correct. Because there's no resultant force, so X cannot be more than Y plus Z. Okay, so that one is okay. Right? That one, your explanation is correct. No, I made a mistake there. I actually wanted to compare with C. A and C look very similar, right? But why
Yeah.
can't C be the answer?
Because the
Okay, so
because
here,
weight will be like weight is always downwards, right? Like weight cannot be Z.
yeah, weight and drag force is now downwards though. Drag force is downwards. Weight is also downwards. Basically this one, Y and Z, yeah, Y and Z are both downwards. The only thing that is really different about this statement here is this one, right? The only thing difference
Yeah.
between A and C is basically this one, right? Correct? Right? Here they say Z
Yeah.
is the viscous drag, Y is the weight of the bubble, where C is saying Z is the weight of the bubble and Y is the viscous drag on the bubble. Both are still acting in the same direction, but somehow they say they switch one to the other. But why is it that the answer is actually A? When you say that the answer is A, that is correct. C is actually wrong, actually. But I just want to explain why, I just want to probe why is C wrong. Okay, so notice that the arrows are drawn different lengths.
Yes.
Y is like this, Y is actually less than Z. Okay, so if I ask you right now, between upthrust, between drag force and weight, which one should be larger? Force and weight, which is larger?
Isn't it the same?
No, it will not be the same. There's one keyword here. It's an air bubble. It's just an air bubble is just a lump of air. So what can you say about air, the weight of air, of an air bubble, no less? It's going to be very little, right?
Yeah.
Okay, so here what you can see here is that because this one is an air bubble, it's just air. Air bubble has very little weight because it is air only. Therefore, drag force will be more than the weight. Okay, so right now you see this one here, y and z. Y is less than z. I know that these two forces are pointing downwards. I know that this is actually the weight plus the drag force. But how do I know specifically which one is actually the weight, which one is actually the drag force? You will actually say that this one is the weight, and then this one is the drag force. You see the length of the arrow because you know that for vectors, the larger the length of the arrow, the larger the magnitude. The smaller the length of the arrow, the smaller the magnitude. So y being the smaller length would be smaller magnitude. It will be the weight. Z being the larger, the longer arrow would have larger magnitude. It will be the drag force. So you would say that Z is the viscous drag on the bubble. Y is actually the weight, whereas X is actually the upthrust, and X is equals to Y plus Z. So this one is upthrust. Okay? So that's the conclusion here, the reasoning here. So C seems somewhat similar, but then there's one small thing that you needed to know. Why is the answer not accepted? Okay, so that should be it.